Hello everyone, welcome to Chemazon-Complete Chemistry. So in today's video, we are going to see the structure of chair conformation of cyclohexane and how we can actually draw the chair conformation of cyclohexane and how do we write down the axial and equatorial positions in a chair conformation. So let us first understand what is the structure of a cyclohexane. It is a six-membered ring cyclohexane where each carbon is what? It is sp3 hybridized, and sp3 hybridized, we know the ideal bond angle should be 109.5 degree, but it is seen experimentally that the bond angle is 120 degree. That is slightly greater than the expected angle of 109.5 degree. Now since it is sp3 hybridized, it is going to be tetrahedral in shape. What does that mean? At every carbon, one of the hydrogen is going to remain below the plane and one hydrogen will be above the plane. Okay, so by looking at the the single bond model, that is the wedge and dash structure, it looks that it is going to be planar. But the question is it really planar? So the correct answer is no, it is not planar because of the electronic repulsions. It does not remain planar, but it assumes a puckered structure. Puckered means slightly non-planar structure. And how does it actually look? It is like this. In this video, as you can see, it is not exactly planar. Some carbons are above, some carbons are slightly lower in position, as you can see in this video. Okay, so now how do you identify the axial and equatorial positions in a cyclohexane chair conformation of a cyclohexane that we have to see? Axial and equatorial positions of the groups in cyclohexane in chair conformation of cyclohexane. So how we can remember that? Just imagine the earth or the globe. We know the axis is what? It is vertical. Okay, so the vertical bonds are going to be what? They are going to be axial. They are called as the axial position or groups present at the axial position. And equator in the earth, you can see it is what? It is horizontal. So the bonds that we draw like this or like this, okay, that is the horizontal bonds. Other than the vertical bonds, they are going to be what? They are going to be the equatorial positions. Okay, so here you can see in this structure, if I want to identify the axial and equatorial position, you can see the three carbons, these three carbons are slightly above as compared to these three other carbons which are slightly lower in position. That is why this structure is called as a puckered structure or not completely planar. Okay, so these red ones are what? They are the axial positions. Okay, red hydrogens are the axial positions. Okay, out of the total 12 hydrogens, 6 are axial. Okay, 6 red ones are axial, and the remaining blue ones they are called as equatorial positions. Okay, this is equatorial, 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 and equatorial. Okay, so we saw just now, all the vertical bonds are what? They are called as axial positions. And the remaining bonds, they are what? They are equatorial positions. Okay, so this was about identifying the axial and equatorial positions. Suppose I want to draw the chair conformation of cyclohexane. How can I exactly draw the chair conformation? So the first step is you have to draw two parallel lines like this. Okay, then draw two more parallel lines like this. Then you can join these two lines. This is the third step. This is the cyclohexane. So as I told just now, the three carbons 1, 2, and 3. These three are slightly above as compared to the other three carbons. So here the axial bonds will be above the plane like this. And for the remaining three carbons which are slightly lower in position, for them the axial bond will be lower like this. So it is alternate above, lower, then again above, then down, then up, and again down. So in this way you can draw the axial bonds. Now it is very important to know how do we draw the equatorial bonds. So as I told you, what is a bond angle? The bond angle is 120 degree. So suppose for this carbon, if I want to draw the equatorial bond, if I draw like this, is it going to be correct? No, because here bond angle is not 120. Okay, suppose if I draw like this, is this correct? No, here bond angle is 180 degree. That is also not correct. So structurally, it is very important that you draw the correct bond angle. Okay, so what is going to be the correct bond angle? It is going to be like this. Okay, the bond angle is how much? 120 degree. Similarly, here also, I cannot draw like this. Okay, this is the correct bond. Then here also like this, 120. Okay, in this way you can draw the axial and equatorial. Now if I want to label them as axial and equatorial, the vertical ones are axial and the remaining are equatorial. Equatorial, this is axial and equatorial. Okay, so in this way you can draw the structure conformation of the cyclohexane. In this, if I want to mark axial, 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 and axial. 6 hydrogens are axial and the remaining 6 are equatorial positions. So here we come to the end of today's video. I hope you have understood how to draw the chair conformation of cyclohexane, why it is not planar because of the electronic repulsion, how to identify the axial and equatorial positions in the chair conformation, and how can we exactly draw the chair conformation. So in the next video, we will see how can we do the ring flipping. What is ring flipping? What are the steps involved in ring flipping? Thank you.